Hello everybody and welcome back. Today we are continuing with our Unit 2, which is all about biodiversity. So today we're going to go over two topics. We're going to go over island biogeography and also ecological tolerance. So you should have downloaded your guided notes for the day. This presentation goes along with those notes, so we can go ahead and jump right into it. So when we talk about island biogeography, first of all, we know that islands are pieces of land that are separate from a mainland, right? And they are completely surrounded by water. Well, islands tend to be colonized by different organisms, and the rate of colonization and the success of those organisms are dependent upon the size of the island and then how close the island is to the mainland. So we've got something called the equilibrium theory of island biogeography. And this is just the theoretical relationship between immigration and extinction of a species to islands, which depends on their size and their distance from the mainland. So if we look at these graphs here, on our x-axis we have the number of species on the island, and on our y-axis we have our rate of immigration in red and our rate of extinction in black. Okay, so typically what we find is that our immigration decreases, right, as our extinction increases. So the equilibrium is that point at which our immigration and our extinction are kind of basically balanced, okay? But these rates will fluctuate depending on the size and also the location of the island. So if we take a look at the immigration of a small island, so smaller islands tend to have less immigration. Now, when I say immigration, I mean organisms migrating from the mainland to the island. Okay, the reason for this is because smaller islands tend to have smaller resources. So you have less immigration to smaller islands. Alternatively, for larger islands, you will typically have more immigration because there are more resources available, okay? And over time, we will see the extinction rate on small islands will be higher than the extinction rate on large islands. And the reason for this, again, is because large islands tend to have more resources that can support more organisms. So it has higher colonization rates, and it also has lower extinction rates. So here's our equilibrium of a small island. And we have typically low immigration and high extinction. And then for a large island, we've got lower rates of extinction and higher rates of immigration. And then here's the difference between a far and a near island. Typically, you are more likely to find organisms on an island that is closer because it's easier for them to make the trip. So the closer an island is to the mainland, the easier it is for the organisms to get there. So you will find more organisms on a closer island than you would a far island. Now this means there's kind of like a Goldilocks island for island biogeography. So in terms of islands itself, the island that will be the most biodiverse and have the most organisms and the lowest rate of extinctions will be large islands that are close to the shore. Okay, so large islands that are close to the shore will have more biodiversity, and small islands that are further away from the mainland will have lower biodiversity. So here's just kind of a depiction of that. So we see here in this first image, we've got a smaller island closer to the shore, and then we've got a larger island a little bit further away. Well, we're going to see more species that colonize the larger islands because there are more resources and there's more habitat space. And then proportionately, fewer species will go extinct on larger islands because there's just more resources available. However, if you have two similarly sized islands and one is further away, you will find more species that colonize the closer islands because it's easier to get there from the mainland. So again, the amount of biodiversity that an island has will be dependent on how large it is. So larger islands tend to have more biodiversity, and also how close it is to the shore. So closer islands will have more biodiversity because they have higher rates of immigration. So the Goldilocks island for biodiversity would be a large island that's close to the shore. So that is the gist of island biogeography. Now let's talk about ecological tolerance. So if you think of you're tolerant of something, you kind of put up with something. So we're going to talk about that in relation to ecosystems. So just a reminder, every species does have a niche. And every species has something called a range of tolerance. So these are the limits to the abiotic conditions that a species can tolerate. So when we say abiotic conditions, sunlight, temperature, salinity, things like that. A fundamental niche is the suite of abiotic conditions under which a species can survive, grow, and reproduce. So a niche is kind of like an organism's job, but it's also the abiotic factors that basically allow an organism to thrive. The realized niche is the range of the abiotic and biotic conditions under which a species actually lives. So the fundamental would be like the optimal, and then the realized would be what the organism can actually live in. It might not necessarily be the optimal conditions, but they can still live and reproduce under conditions that maybe are not so ideal. And then when we talk about distribution, those are just areas of the world in which a species lives. So every species does have an optimal environment in which it performs particularly well. So again, there's a range of this tolerance, right? So this peak right here would be where the species is in their basically fundamental niche. So this is where they can survive, grow, and reproduce. Everything's perfect, they're great. And then there's a range on either side of this where they can survive and grow. And then when you get kind of to the upper limits of that tolerance range, these species are just surviving. So if we think about our hierarchy of needs, these species are basically getting food and water, but they're struggling to survive, so they can't really focus on growth and reproduction. A niche generalist is a species that can live under a wide range of abiotic or biotic conditions. These organisms tend to be hardy. Think of like cockroaches. Cockroaches are generalists. They will probably be here long after humans die out. They could probably survive a nuclear war. I hate cockroaches so much, but they are generalist species, and they adapt and survive well in a large range of climates. A niche specialist is a species that is specialized to live in a specific habitat or to feed on a small group of species. Specialists tend to be more complex, and also they are more susceptible to ecological disturbance, because if one thing in their ecosystem gets messed up, it is very likely that they can be injured or even die. So niche specialists do well when environmental conditions remain constant. However, loss of a favored habitat or food source will leave them with few alternatives for survival. Generalists do tend to fare better under changing conditions because they have a number of alternative habitats and food sources available. So a limiting factor is an environmental condition which limits growth, distribution, or abundance of an organism or population within an ecosystem. This typically restricts organisms from occupying their fundamental niche, which is the optimal, and results in the fulfillment of their realized niche. Okay, so if we take a look, this is niche partitioning in warblers. So we have different kind of warblers, which are these teeny tiny little birds, and we have their niches in this tree. Okay, and basically we've got these partitioning. So remember, resource partitioning is when organisms will kind of they will basically rule out the competition, if that makes sense. So these different warblers might be adapting to eat different types of organisms in order to avoid competition with the other warblers. Well, because they are having to maybe find other food sources, they are not able to realize their fundamental niche because they're having to work around the other warblers, and they are in their realized niche. So maybe this little guy is eating smaller worms because he doesn't want to compete with this guy right here, but in doing so, he's not getting as much nutrition as he possibly could. He's still surviving and he can still grow, but he's not in his full total fundamental niche. He's in his realized niche, which is kind of like the harsh reality that organisms often have to face. So ecological tolerance basically just refers to the range of conditions, such as temperature, salinity, and sunlight, that an organism can endure before death or injury may occur. Okay, so what can organisms tolerate until they become injured or die? So this picture here shows changes in tree species distributions over time. So pollen recovered from lake sediments indicate that plant species moved north as temperatures warmed following the retreat of the glaciers. This began about 12,000 years ago. So areas shown in color or white were sampled for pollen, whereas areas shown in gray were not sampled. So basically what this is showing is that over time, these trees were adapted to cooler temperatures, and then as our Earth warmed and those temperatures started to warm up near the equator, these trees actually migrated north, right? So we would see higher distributions of these trees in climates that remained cold. So this is just a response of these organisms to the change in their environment. So their fundamental niche would be to be in cooler climates, and therefore they would have to move in order to kind of remain in their ecological tolerance range. So there's a difference between resistance and resilience. So resistance is how much a disturbance can affect the flows of energy and matter. If there is an area with a high resistance, this is when a disturbance influences populations and communities, but there's no effect on the overall flow of energy and matter. So if there's something that happens like a forest fire or some kind of disruption in the ecosystem, individual populations can be affected, but overall the energy flow remains stable. Resilience is the rate at which an ecosystem returns to its original state after a disturbance. So high resilience means that ecosystems can bounce back and return quickly. So here's an example of a pre-fire vegetation. So it's pretty high. And then we have this forest fire that breaks out thanks to gender reveal parties, right, in California. But we have this fire that breaks out. And because of this, our vegetation dips down really low because it's destroyed in the fire, okay? Here's the recovery rate. So over time, this vegetation recovers, and then we get to our post-fire vegetation. So the resistance is how much the disturbance affects the flow, and then the resilience is the rate at which it returns. So this recovery rate would coincide with the resilience, and the resistance is how much disturbance actually occurs. So environmental change causes species in extinction. So if environmental conditions change, species that cannot adapt to the changes or move to more favorable environments will eventually go extinct. The average lifespan of the species appears to be only about 1 million to 10 million years, and 99% of the species that have ever lived on Earth are now extinct. And we have experienced several mass extinctions, and this is just a large extinction of species in a relatively short period of time. So there have been 5 global mass extinctions, and in our previous lesson we kind of talked about how scientists think we're in the middle of a 6th one, and a lot of that is driven by humans that are altering the environment. So with our global warming and our continued combustion of fossil fuels, we are driving a very increased extinction of organisms. And these extinctions were caused by, natural events. Everyone knows the dinosaurs were wiped out by a meteor, a large one that hit the Earth. So it wasn't the impact itself that caused the die-out of the dinosaurs. It was actually the changes in the climate. So all the ash and the dust temporarily changed the climate and covered the amount of radiation that could reach the Earth. So productivity lowered. And then there was a rapid change in the climate which the dinosaurs could not adapt to, and they died out. This is why all life did not die out at this time. So, those generalists that were around during the dinosaur eras, they were able to adapt to that, and they were able to live through it, and then evolution continued. So just something to keep in mind as we go through biodiversity and we think about the kind of things that can lead to a decrease in biodiversity and extinctions. So that is all I have for you guys today. If you have any questions, please send me an email. And if not, I will see you in the next one.